let's start by reviewing quantum mechanics again. So in quantum mechanics, every piece of matter or energy can be described by an element of a Hilbert space. The Hilbert space is a generalization of a concept where we're very comfortable with wave functions. Now we can be comfortable with other things like states of polarization, states of spin, anything like that. When we take a measurement of a quantum system, we get a probabilistic jump. We get a wave function collapse, and each measurement is characterized by an observable. And the observable has eigenvectors and eigenvalues, and the eigenvalues are the answers we might get when we make the measurement, and the eigenvectors are the state we'll then be left in. And so an eigenstate of an observable is a state that has a definite value if you were to make a measurement of that observable. And the only other postulate we need is the fact that states evolve, these elements of the Hilbert space evolve according to the Schrödinger equation. The Schrödinger equation has the Hamiltonian as an operator in there. The Hamiltonian is indeed an observable. It's the observable for energy, but we can see that that basically tells us everything we might need to know in order to predict the future. If you know the whole state, you know what happens if you make measurements, and you know how the state's evolving, then you know everything. We then went in and had a look at some details and some effects of the fact that the evolution in quantum mechanics is linear, and we noticed that we could therefore describe the entire evolution in terms of an operator, the time evolution operator. The time evolution operator turned out to be unitary. And we also noticed that the only way we actually extract information from quantum mechanics is through this measurement postulate, and another way of looking at that was through expectation values, averages of particular observables. So if I know the average of an observable, say the position variable x, and I also know the average of x squared and x cubed and so forth, then I in fact know the complete probability distribution for measuring x. And so all experiments that we can do can be characterized by knowing the results of expectation values, just as they are characterized by knowing the actual results of measurements. And we look at that and we see that the expectation values can be described if we look at the operators and the states. We can either associate the evolution with the operators, which is the Heisenberg picture. This is how Heisenberg went about creating quantum mechanics. He felt that was very natural because we're used to thinking of things like position and momentum changing with time, whereas in the Schrödinger picture, which is typically in fact the picture that most people first learn quantum mechanics in, it's the states that change in time. And so the only reason the position seems to be changing is that when I apply the position operator to this state that's changing, then I get a different answer. Okay, and so we can see that both pictures are exactly the same. They both give the same predictions, but some are easier than others to do certain calculations in. One advantage of the Heisenberg picture is that you have this really direct connection to expectation values. One advantage of the Schrödinger picture is you don't have to keep calculating the evolution of a large number of operators. You can just do it for one state once and you know everything. And we have at the bottom of the screen there a few examples of things that we derived using either the linearity of the evolution or our definition of the Heisenberg operators, which is just applying the evolution operator on either side of the operator. All these commutators are really handy results that turn up again and again and again. Still to come in quantum mechanics, we're going to revisit some key aspects of classical mechanics and how they fit into quantum mechanics. In particular, we're going to look at action and the role of the Lagrangian, which is a very important part of the correspondence principle, but we've never hit it before. We always have seen the Hamiltonian turning up, but the relationship between that Hamiltonian and the Lagrangian is not very clear. We're also going to revisit the idea of symmetries, this very deep and far-reaching idea, the fact that symmetries in our system relate to conserved quantities, and we're going to look at symmetries and their role in quantum mechanics, and then finally we're going to look at some calculational methods. But before we do all that, we're going to revisit this idea of Schrödinger pictures and Heisenberg pictures and know that there's one possibility that we haven't yet considered. So we got our different pictures from looking at the different ways we can break down the idea of an expectation value. So this is a physical thing, so our theory always has to get this right. But we can break it down in different ways. It depends on the state, it depends on time, and it depends on the operator. Now, the Heisenberg picture is to group all these together and call that the Heisenberg operator of A and assume that all the operators are the things that are changing in time and the state is static. The Schrödinger picture is where you assume that the states are evolving, so you group the evolution with the states and you call the operator static. What about the obvious other possibility, which is the interaction picture, where in fact both the operators and the states evolve in time? When would you want to do that? You might want to do that if you had a Hamiltonian that had two parts. So you might have a Hamiltonian, this is the correct Hamiltonian, the full Hamiltonian, and it involved one Hamiltonian that you knew well and had characterized well, and some different one that would otherwise mess up your understanding of this one. So these are the two parts. This is often called the interaction, which is why it's the interaction picture. Then we can define a unitary operator based on just this part of the Hamiltonian. So if this is a constant Hamiltonian, then the unitary operator is just the exponential of this. If we only had that part of the Hamiltonian, then our unitary operator, and I'll call that U naught, like H naught, would just be the exponential using H naught. Just as the full Hamiltonian generates a time evolution operator that's unitary, so too a smaller Hamiltonian, just this H naught, would also have generated a time evolution operator that's unitary. And this exponential operator here is unitary. And so that means that U naught dagger is 1. And so we can insert 1 into here, and we get, which is long, but we can now see that we can break it up differently. Rather than breaking it up into all of this being the Heisenberg operator and that being the Heisenberg states, or all of this being the Schrödinger state and this being the Schrödinger operator, we can break it up into smaller pieces. We can have time evolution in our operators like that, and we can have time evolution in our states. And so in the interaction picture we have both evolving operators and evolving states. So we can define all interaction operators like this, where T naught was just the time where the operators are equal to the Schrödinger operators. So that's a definition. We can also define the states like this, which, because this is just the normal time evolution operator we'd use to define the Schrödinger picture states. Now we can take the derivative of these states with respect to time, and we could actually work out the evolution of time evolution operators from the Schrödinger equation, but you could also do it directly from this exponential. Because any function of an operator commutes with that operator, then you can actually take out the H naught either to the left or the right, it doesn't matter. But the rest of it all comes out just like the normal derivative. And this is explicitly the Schrödinger equation. And now we can see that this term here and this term here, the H naught parts, actually cancel. And in order to do that, you actually have to be able to commute these two. So you have to put the H naught on the other side of the U dagger naught. But you can see that that's true because they commute. So those terms cancel, and you're just left with, which again isn't quite anything we can use. But if we insert a 1 here based on the U naught, if we put in a U naught and a U naught dagger in there, you can immediately see that this is the interaction picture state, and that this is the interaction picture version of V. So what have we learned? We've learned that if you put all the operators into the interaction picture, then the evolution of the interaction picture state just evolves exactly like you'd expect the normal Schrödinger equation to evolve, except that you don't have to worry about the H naught anymore. So in some sense, we've kind of pulled all the evolution of the H naught terms in the Hamiltonian into the operators, and the effect of V is in the states. And that's the interaction picture. And sometimes that's a lot easier to work with in a calculational sense than either the Schrödinger or the Heisenberg picture, because sometimes that splitting of the evolution of one part of the Hamiltonian and the other part is really handy.